subject proper, you can say, where you will get to solve certain equations, nonlinear equations. And we'll see what kind of techniques or numerical methods are applied for solution of nonlinear equations. If you can see the screen, just let me know. Is it visible?
Yes, sir, it is visible.
Okay.
Sir, I think Ananya is trying to join, sir.
I think I let her join, I think.
Join করেছি.
She has joined. Okay, no problems. Okay, so let's start today's class. Hello and welcome to this numerical analysis lecture, where we will discuss about solution of nonlinear equations. The focus in this lecture is on iterative methods to solve such equations, and two different iterative methods, bisection method and Newton-Raphson method, would be discussed. These two techniques are two different types of techniques, because the bisection method is called something as a bracketing method, whereas the Newton-Raphson method is known as an open method. So what are these techniques? We will discuss them in detail. But the starting point for today's lecture is this familiar flow diagram that was discussed in detail in the introductory lecture. It shows how one moves from problem definition towards obtaining a solution and its subsequent implementation or application in a societal context. However, the first and the probably one of the most important aspects of this is the conversion of the problem at hand, or the problem definition, you can say, to an abstract model that allows for some mathematical analysis. What it means is that conversion of the physical model to a mathematical model. And how this is done? How do we convert the problem definition to a mathematical model? This is done with the help of theoretical knowledge. You can say basic scientific and technical knowledge combined with, of course, the common sense, and augmented by experimental as well as observational data. Now, these mathematical models that describe the system behavior are often in the form of equations. Maybe a single equation, or it may be multiple equations or a set of equations. And they are known as, depending on whether there is a single equation or set of equations, as the governing equation or governing equations of the system. And these equations can take up various forms, from simple algebraic equations, polynomial equations, transcendental equations, even differential equations, where again there could be ordinary differential equations or partial differential equations. There can also be a distinction made in the form of linearity or non-linearity. That means these equations well be linear equations or they may be non-linear equations as well. But whatever the form of these equations, once they are obtained, then the focus shifts to obtaining solutions for them. How do we solve these equations? And that is where numerical analysis comes in as a problem solving tool. Of course, depending on the nature of the equations, there can be various different classes of numerical techniques. There could be different classes of problems. As just now we mentioned, there could be algebraic equations or differential equations. Similarly, there could be different types of numerical techniques to tackle those different classes of problems. So as you can see here, numerical techniques exist for solving nonlinear equations, linear simultaneous equations, ordinary differential equations, etc. Now here I have only highlighted or emphasized on these three types only because they are included in our present syllabus. There are, of course, other types of equations or equation systems, but they are not in focus right now. And in terms of today's class, out of these, we will look at, as already mentioned, solution of nonlinear equations. The other topics will, of course, be definitely dealt with and discussed in future classes. So how do we solve nonlinear equations? That is the question now. There are two approaches. Two approaches to solve these nonlinear equations. The first one is the direct method, or a method where closed form solutions are obtained. Here the solution is given in terms of an expression, a closed form expression, which contains the coefficients or parameters present in the equation. Let's take an example, a very well-known example. This is a quadratic equation. Ax square plus bx plus c equal to 0. Quadratic equation, of course, is a nonlinear equation because it contains the second power of x. And we are, from our school days, quite familiar with the closed form solution of this quadratic equation. This, as you know, is minus b plus minus root over b square minus 4ac whole divided by twice a. So what does this expression contain, this solution contain? It contains a, b, and c. What are a, b, and c? These are the coefficients of the quadratic equation. You can clearly see it in the expression that is given there. So once this closed form solution is obtained, whatever be the values of a, b, and c, you can just simply put them or substitute them in this closed form expression and obtain the values of x. Obviously, there would be two roots, so you will get x1 and x2, depending on whether you are considering the plus sign or the negative sign. That is the advantage of closed form solution. That is, once you have solved this, then it is true for all values of the coefficients a, b, and c. Of course, you need to also keep in mind that if a becomes equal to 0, then this closed form expression loses validity, because then there comes a question of division by 0. But in any case, if you look at the quadratic equation, if a becomes equal to 0, then it does not remain a quadratic equation at all. So that is not a valid situation to consider. So let's move forward. Now, similar closed form solutions, expressions, or you can say formula also exist for cubic and quartic polynomial equations. That is, equations containing x cubed and x to the power 4 terms. Was he able to join? Not sure. Maybe he will come in later again. So as I said, similar closed form formula is also available for cubic, that is an equation containing x cubed term, and quartic, that means equations containing x to the power 4 terms. But these forms or these expressions are not that popular and they are not familiar to us. Certainly not as familiar as the quadratic equation closed form solution. So what is the advantage? If a closed form solution can be obtained, then that is possibly the best scenario that you can think of. Then for any value of the coefficients or parameters, they can simply be substituted, as I already mentioned, into the closed form expression, and an exact solution can be obtained, can be found. However, closed form solutions are difficult to obtain. They are difficult to obtain most of the time. Specifically for higher order polynomials or polynomial equations and transcendental equations. That means equations containing logarithmic or trigonometric terms. The mathematics involved to get closed form solutions in those situations are often quite complicated. In fact, there are certain cases, some cases may be present where it is impossible to obtain the solutions. That is, impossible to obtain the solutions as a closed form expression. So what's the alternative? How do we get the solutions for such cases? There has to be an alternative approach, and that approach is known as the trial and error method. Now we have a notion, maybe a preconceived idea, you can say, that trial and error methods are very general. They are random and they are not quite sophisticated. But that is not the type of trial and error method that we are talking about here. Instead of considering random guesses, we will consider a logical basis on which we can decide upon a successively improving series of guesses or approximations. Our idea of trial and error method is that we have an equation, we consider a solution, suppose x equal to something. For that equation, we put it into the equation, substitute it into the equation and see whether it equates to 0, whether it satisfies it or not. If it doesn't, we discard that value of x, we take a new value of x. Now you can think that this could be quite arbitrary. Choosing of x, choosing of that solution, approximate solution, could be quite arbitrary. But it is not the case that we are going to consider. We will consider a situation where we will start with an initial guess, and from that initial guess, we will logically proceed towards the actual solution, the exact solution, in a series of steps. And those steps are going to be repeated over and over again. That is why these trial and error methods are also known as iterative methods. Iterations obviously refer to repetitions. Because of the repeated nature of these trial and error methods, we call them iterative methods. So how do we define an iterative method? It is a repetitive mathematical procedure that generates a, you can say, sequence of improving approximate solutions for a class of problem. And this is based on an idea of successive approximations. Here, in this definition, do note the use of the phrase improving approximation. It indicates that there is nothing arbitrary about the process, and there exists a certain well-defined approach, a well-defined logic that directs the guesses or approximations towards the actual solution of the equation. Schematically, if we represent this process, you can see that there is an initial guess. That is the starting point. And final step is the obtaining of the approximate solution, which is also known as a final approximation. So starting with the initial guess, we gradually move towards the final approximation. What is in between? In between, there are a series of sequential steps which are repeated. Each repetition of these steps, or you can say each repetition of these sequence of steps, starts with an approximate guess value, and ends with another approximate guess value. Hopefully, an improved guess value. Now here comes the question, how do we know that the guesses are improving or approaching the actual solution? I can qualitatively say that it is improving, but I have to justify that statement by some quantification. How do we do that? Of course, we keep track of the relative approximate error. If the error keeps reducing, we are on the right track. We are approaching the solution. Obviously, if the error is not reducing, it is blowing up from iteration to iteration, then something is wrong with our numerical method. Now, the guess value obtained at the one set of repetition acts as the starting approximation of the next step. So we had an initial guess. We perform a sequence of steps. At the end of those steps, we obtain another approximate value, hopefully an improved approximate value that approaches the solution. This can also be checked in terms of an relative approximate error. Now, this approximate value is going to be the starting value for the next set of sequential steps, which are repeated. And like that, it will continue till the approximate relative error falls below a predefined limit. And that is when we say that the final approximation or the approximate solution has been achieved. So this is basically how the iterative method works in general. One thing that we have established is that it is repetitive in nature. And as a result of that, they are quite laborious, time consuming, and not to mention, quite simply, boring. These are difficult to solve by hand, and because of the nature of these calculations, laborious, time consuming, boring, uh, doing these by hand is generally disliked. Suppose those sequential steps that are to be repeated, they are to be repeated 100 number of times, or maybe even more than that. If you do it by hand, definitely you will lose your efficiency after a few steps. So that is a problem with these kind of iterative methods. But of course, we can take help of computers. We do not need to solve these problems by hand. Such a procedure can be expressed concisely as a computational algorithm, and it becomes amenable to implementation through a computer program. We know what an algorithm is, which has been already covered in your previous courses. And if you can express the method that we have just described, the general method or general procedure of solving iterative problems, if you can convert it to a computational algorithm, then you can obviously develop computer programs on the basis of this, and you can give the task of doing all those calculations to the computer. The scope for human interference reduces quite drastically, and the job of the user or the human would here be to just supply the initial guess, and the rest would be taken care of by that algorithm and the computer. So that is the advantage of such numerical methods. It is also possible to formulate generalized algorithms. Let me give you an example here. Let's say we have a system of linear simultaneous equations. We have n equal to 3. That means 3 equations are there, 3 unknowns are to be solved. There are numerical methods which are available that can be converted into computer program to solve these set of 3 equations. Now suppose the equation changes and n becomes equal to 5. So now we have 5 equations and 5 unknowns. Should you write another program to tackle this new system having 5 equations, 5 governing equations? It is possible to generalize your program in terms of that parameter n, so that at the beginning of your program code, you will ask the user what is the value of n, whether n is equal to 3 or n is equal to 100. And according to that, you can design your code in such a way that it will be able to handle various different values of this parameter n, where n is the number of equations. So that is what is meant by you can generalize these algorithms to solve a class of similar problems. There is also the added advantage of these iterative or trial and error methods, that here the errors are negligible. Errors are negligible as compared to the procedures based on the exact methods or closed form solutions. It is quite easy to understand because you are actually keeping track of the errors, and the iterations are in fact driven by the amount of error. If the error is larger than a specified value, then you go for more number of iterations. And if that error falls below the specified tolerance, then you stop the iterations. So automatically the errors are going to be reduced. So that is why inherently these iterative methods do not suffer from the ill effects of rounding errors. That is an added advantage. Now let us talk about in more detail of solutions using iterative methods. What is the objective? The objective is to find out solutions for the general equation fx equal to 0, where this fx for today's purpose is at least a nonlinear function. What is meant by a nonlinear function is that there would be different powers of x in this function fx. It will be a linear one if the exponent, the power of x, is 1. So if I have an equation ax plus b equal to c, this is simply a linear equation. So we can say that if the powers of x maximum, it goes up to 1, and the coefficients of x are not functions of x, that means here a is not a function of x, it's a constant, then it constitutes a linear equation. However, if we consider this, then this is obviously more than 1. X squared term is there, so this is nonlinear. You can define this as an expression or an equation having powers of x more than 1 and or having coefficients of x which are functions of x. So that is the definition of a general nonlinear function. So fx here is a nonlinear function, and what we are looking for is the roots of this equation fx equal to 0. What is meant by the root? It means that we are looking for a value of x which, when substituted in this equation, would evaluate to 0. So that is the solution or root of the equation. If you want to apply a successful iterative method, we need to consider certain basic points. In fact, these basic points are relevant to all different iterative methods. What are these points? Let us see one by one. First of all, where to start this iterative cycle? The initial guess. What is to be chosen as an initial guess? It is a very important aspect for this iterative method, because if you choose an inappropriate initial guess, then it might lead you away from the actual solution. You need to have a good idea about what can act as an initial guess for these sort of methods to be effective. Next, how to proceed from the initial to the subsequent approximations or guesses. We have the initial guess, fine. Now, how do we get the next guess? It is, as already mentioned, not arbitrary or random. So there has to be a well thought out process, a sequence of steps through which the next guess, the subsequent approximation, is to be determined. So that needs to be thought about in quite detail. Next is, how fast do these approximations converge to the solution? how many iterations are going to be there, how many number of times those sequence of steps are to be repeated. Is it 10 times, 100 times, or 1,000 times? So that means that there is a rate of convergence. Some of the numerical methods would converge to a solution very quickly, but others can be quite slow. They will approach the solution definitely, but it does in a very slow manner. It takes time. It takes more number of iterations to reach the actual solution or reach the vicinity of the actual solution. Then also we need to consider how much computational effort is required in each iteration. Now, the computational effort can be measured in terms of function evaluations. Fx is a function, nonlinear function in this case. So, in the course of the calculations, even in the computer, there has to be function evaluations. Put the value of x in the function, evaluate its value, get its value. So, how many number of times this function evaluation is taking place in each iteration? So, that is a measure of computational effort. If it is too large, then your system might suffer. That means a system having low computational capability cannot handle numerical methods or iterative methods with high computational effort. So this point needs to be dealt with as well. And finally, when to end the iterative cycle, when to terminate the iterative cycle. This is also known as the termination criteria. We start with an initial guess. That is fine. But how do we end it? We have already given an idea about when to end this iterative cycle. That is when the error, relative approximate error, falls below a given limit. So usually that acts as the termination criteria. So these are all the points, all 5 points that are relevant for different iterative methods and should be answered before you try to implement these in a computer. Now, what are the different types of iterative methods that can be used for solution of nonlinear equations? Here you can see a list: bisection method, method of false position, which is also known as regular falsing, Newton-Raphson method, the second method, Muller's method, there's Chebyshev's method. A whole host of different methods are present that deals with solution of nonlinear equations. Our focus is on these two, the bisection method and the Newton-Raphson method. As already mentioned, bisection method is it falls amongst a class of problems known as bracketing method, whereas the Newton-Raphson method is a separate class of iterative methods which are known as generally as open methods. Now let us start with the bisection method. But before we go to the bisection method itself, we have to learn about the intermediate value theorem. What does this theorem say? It states that if fx is a real and continuous function in some interval xl to xr, where xl represents the left hand edge of the or left hand interval of the domain, and xr is the right hand side of the domain. And if this product f of xl multiplied by f of xr gives a negative value, then the equation fx equal to 0 has at least one root in the interval. By the way, I should mention one real root in this interval xl xr. Let us see this graphically. That would probably clarify it just a little bit So here we see the Cartesian coordinate system. The horizontal axis is x, and we plot the values of fx, the functional values, along the vertical axis, the y-axis. And here is a general function fx, arbitrarily chosen, and we have the domain interval as this. So we have xl here. The functional value corresponding to xl is f of xl, and on this side we have xr, the right hand side. The functional value is f of xr. Quite clearly, here the value is negative, functional value is negative. Here the functional value is positive. So quite obviously, it will satisfy this condition where product of f of xl into f of xr is negative. One of the values is negative, the other one is positive, so the product will be negative, that is less than 0. And what it says is that if that is the case, the condition is satisfied, then there has to be one root within that interval. And you can see the root over there highlighted in blue. If you think about it, it's quite simple really. At one point, the function has a negative value. At a later point, the function has a positive value. So in between, it must have crossed the x-axis. When it crosses the x-axis, the function has a value of 0. So that would be the solution to the equation. That is the root. So this is what is stated in the intermediate value theorem. And as you will see later on, in the bisection method, the intermediate value theorem is applied repeatedly. So that is the basis for the bisection. But before we go to that, let us look at certain other examples of different functions in this xfx plane. So you can see here that in this interval, xl, xr, we have a functional value, positive functional value here. We have a positive functional value here. So obviously, this condition is not satisfied. Both are positive. So the product cannot be less than 0. And you can clearly see that within this interval, there is no root here. The root is somewhere around this side. Similarly, if the interval is chosen in such a way that both the values are negative, both are negative here. This is negative, this is negative. So their product would give us a positive value. Again, it does not satisfy this condition, and we can clearly see that there are no roots within this interval. What about here? XL gives us a positive functional value, whereas XR also gives us a positive functional value. But here we see that within that interval, we have two roots. So does it violate the intermediate value theorem? In fact, it does not, because you can see that it does not satisfy the condition mentioned in the intermediate value theorem. Here, the functional product of the functional values are both, because they are both positive, the product comes out to be positive as well. So it does not fall within the realm of the intermediate value theorem. Let's consider this one. Here we have f of xl as positive and the f of xr on the right hand side is negative. So it satisfies the condition given in the theorem. This condition is satisfied. But how many roots are present here? At three different places, this curve fx crosses the x-axis. So that means there are three different roots present here. So does it violate the intermediate value theorem? No, it does not, because you can see here that it says at least one real root would be present. In fact, you can generalize this statement and say that if this condition, that is product of f of xl and f of xr, is less than 0, then within the interval xl xr, you would find odd number of roots. This product is less than 0, then within this interval, you will find odd number of roots. That means there could be one root, could be 3, could be 5, but odd. I hope this intermediate value theorem is clear to you, because as I said, in bisection method, this theorem is applied repeatedly. This bisection method is also known as the binary search method. Already mentioned that it is based on repeated application of the intermediate value theorem. Also, previously mentioned that it is a bracketing method because it involves finding a root between 2 points, that is 2 brackets, and that bracket is given by the interval that we were discussing just now. An interval is defined in terms of its left hand side and the right hand side, and those two are the ones that make up the bracket for this bisection, and hence it is called a bracketing method. In a concise form, this is what the bisection method does. This method is applicable for numerically solving equations fx equal to 0, where fx is a real, nonlinear, continuous function. It has to be continuous within that interval xl and xr. It has to be real valued. And of course, because of the previous assumptions that we have made, this is a nonlinear equation that we are trying to solve. So if fx is a continuous function defined within this interval xl, xr, and where fxl and fxr have opposite sign, then in this case, xl and xr are said to bracket a root. So this is, in fact, a restatement of the intermediate value theorem in terms of the bisection. Now we will try to graphically establish this method and what it does, and then we will go forward with an example and try to develop the algorithm for this method. So what it does is quite clear. Let's say this is a function, nonlinear function, fx, and the iterative cycle is started by choosing the 2 bounds, the 2 extremities of the interval. So this gives us the initial search interval bounded by xl on the left hand side and xr on the right hand side. So you have the xl and xr as shown in this graph. The functional values, of course, are also written over there. What is the condition? The condition is that sine of f of xl cannot be equal to sine of f of xr. If it is equal, obviously, then the intermediate value theorem does not apply. You cannot apply the bisection because there would not be, possibly there would not be a root in between that interval. So the first step is to choose the appropriate interval. How do we know that it is an appropriate interval? You have to satisfy the condition that is given there. So sine of f of xl should not be equal to sine of f of xr. And that can be guaranteed, assured, if you satisfy this expression. Product of f of xl and f of xr is less than 0. So that is the initial search interval. Now, how do we approach the root? We will bisect the interval. We'll bisect the interval and find out f of xm. So if we bisect it, we obviously get two new intervals from xl to xm and xm to xr. This is the bisection point. And you get the functional value at that point as f of xm. Quite obviously, xm has the value of xl plus xr whole divided by 2. Now, as I said, we get two new intervals. We have one root in the original interval. So obviously, that one root would reside in one of the new intervals. It cannot be in both of them, is it? It will be in one of them. So what we will do is we will retain the interval that contains the root and we will discard the other interval. For example, in this graphical scenario, you can see that the root is clearly situated in the interval xl to xm. You can also mathematically guarantee this if you multiply f of xl with f of xm and see that the product comes out to be negative, less than 0. So what do we do with the other interval? It's not any use to us. So you can discard that interval. And with this new interval, xl to xm. So here it is mentioned that if f of xl multiplied by f of xm is less than 0, then you define a new bracket. And this new bracket is xl to xm. However, if this condition turns out to be false, that is f of xl multiplied by f of xm is greater than 0, then obviously it means that the root is not within xl to xm. It will be in xm to xr. But the example that we are showing at the moment, it is the root is situated within xl to xm. So you can see that now the part where it is not there, so xr to xm, that is xm to xr, I should say, that is completely written off, disregarded, and we move the right hand side interval to the previous position of xm. So this is our modified search interval. And that is the algorithm that is implemented to ensure that in each interval, half of the previous interval is discarded. That is the modified search interval. If we apply the same thing again, you find out the xm value, that is the midpoint of the search interval, and repeat the process. So that is f of xm. Now you see that the root is situated within xm to xr. So you can discard this part and further half the search interval. This becomes the new search interval. And the process would be repeated. Do it again. As the process is repeated, width of the interval becomes smaller and smaller, and it approaches the root of the equation. Zeroes in on the root of the equation from both sides, depending on which condition is satisfied. That means at each of the steps, we need to check this condition. And if it is satisfied, we will move one of the edges of the search interval, move the right hand side here, and if this is not satisfied, then we'll move the left hand side of the interval. But at each iteration, one of the sides is moved towards the solution. So as a result, in each iteration, the width of the search interval gets halved. It becomes smaller and smaller so that it approaches the root in the middle. When do we stop this? When the search interval becomes smaller than the pre-specified error limit. So obviously we have to keep track of the error as well. So we'll check the error at the end of each iteration. If it is above the pre-specified tolerance, then we repeat the procedure again. And if it is smaller than the pre-specified tolerance, then we have reached our termination criteria and we will stop the iterations. Once we stop the iterations, then we have one XL, one XR. So what is the root? The root would be the midpoint of the last search interval. So you can see here the last point, midpoint of the last search interval is the desired approximation to the root. But there is a condition that needs to be considered. I have not talked about that. What if this f of xl multiplied by f of xm becomes equal to 0? It is possible. We have chosen the guesses quite randomly. Of course, satisfying the condition that is one of them should give a negative value, functional value. The other one gives a positive functional value. That is fine. But as the computations progress through different iterations, it is quite possible that one of the functional values come out to be 0, and then this product becomes equal to 0. Can you tell me what is the significance of this?
So 3 roots are there.
XM will be the
Can you repeat it?
Sir, including those 2 bounds, there will be another root. I mean 3 root will be there, sir.
Not necessarily.
sir. XM will be the root in this case.
XM and XL as can be as well as a root.
One of the edges of the domain, that is one of the sides of the interval itself, is the root.
Yes, sir.
That means you have shifted, say, XL to a new position. Now that XL is probably itself the root or very near to the root. Then this might happen. So if you write a program, you have to take care of such situations as well. So keep that in mind. Now we talk about the termination criteria. I think we have talked about this quite a lot in general terms, as well as in case of the bisection method as well. We stop the iterative cycle if the search interval becomes smaller than the predefined error limit. How we can express this mathematically? The search interval is XR minus XL. We divide it by XR to get the relative approximate error. and we convert it to percentage, compare it against a pre-specified value, where epsilon A is the pre-specified tolerance on the relative error. If this condition is satisfied, then we stop the iterations.
So we have to define the EA beforehand, right, sir?
Yes, it has to be defined before you begin the iterations. Now, here is a statement that says the approximated root has error not greater than the half of the length of the interval of which it is the midpoint. Now, sounds complicated, but it definitely is not. Let us consider this interval. Here is XL, here is XR. Let's say this is a modified interval towards the end of the iterative procedure. That means we have cut down the initial search interval to a very small value, and we have arrived at this XL and XR. Within this small interval, the root is here. Let's represent it as capital R. Capital R is the actual root. So we know that the midpoint of the final interval that is obtained, that is the approximation. So this is XM. XM is definitely XL plus XR by 2. Now the final error, of course, within this specified limit is this amount. This is the error, let's say E. Now what could be this maximum value of this error? The maximum value could be when R is very near to this edge. If R moves to this XL, towards this XL, is very near, almost on top of XL, but not exactly XL, then we have the maximum error from XM. Same thing could happen if this R is situated on the right hand side, here, very close to XR. Then that is the maximum amount of error that can be obtained. So how much is this E? E is going to be always less than the half of the length of the interval, because XM is right at the middle. So the maximum that E can be is probably just a bit less than the half of the length of the interval. So that is what is meant by this statement. But here we need to consider another termination criteria as well. This is also a valid termination criteria. We can stop the iterative cycle if we find that the functional value is less than the pre-specified tolerance. Functional value is fx. If this fx comes out to be less than a pre-specified tolerance, that means fx is very, very close to 0. Then also we can stop the iterative procedure. That is also a valid termination criteria. And on the right hand side, although obscured by the previous explanation, we have the definition for epsilon t, which is known as the pre-specified tolerance on absolute error. So epsilon A and epsilon t are quite different, and they are applied to two different parameters. One for the relative approximate error, the other one is applied for the functional value itself. So both are appropriate termination criteria. Now, how many number of iterations?
So epsilon theta epsilon theta.
Epsilon t is the pre-specified tolerance on the absolute error. It's also a previously determined or previously decided value. But it is not same with epsilon A, because that tolerance is applied on the relative error. Here, this is applied on the true error. This is relevant to true error. So there is the difference. Now we move on to the number of iterations. How many number of iterations are to be performed to obtain the required level of accuracy, to bring the errors down to the predefined limit. That can also be mathematically obtained. The reduction in each interval is basically by half. So if the original interval is XR minus XL, then the modified search interval is quite obviously XR minus XL whole divided by 2. And this is true for all the iterations, right from the start to the end. In each of the iterations, the search interval is getting half. So after n iterations, we would reduce the search interval by how much? 2 to the power n times. Simple mathematics. In one iteration, it is reduced by a factor of 2. So in n iterations, it will be reduced by a factor of 2 to the power n. And if epsilon t is the predefined error limit on the absolute value of the interval, then approximately the number of iterations can be obtained through this formula. So XR minus XL is the original interval that is divided by the factor 2 to the power n. That means it gives by how much the reduction, by how much it has been reduced, and that has to be less than or equal to the absolute predefined error limit. So we can simplify it to get an expression for n, which is like this. So it's an important expression. Please keep it in mind.
এটা যে ইন্টারভেল, তাহলে এটা লেস দেন এপসাইলন এ হতো না, কারণ এটা তো এফ অফ ওইটা নয়, তাহলে এপসাইলন টি কি করে হলো?
This is written as epsilon t because let's say we have two types of error. Okay, let's say epsilon is XR minus XL. This is the true error. Okay, let's say this is compared with epsilon. So what we are comparing it here with is not the relative error. So if I write it out, this will be XR minus XL divided by 2 to the power n, which is going to be less than, this is XR in say nth interval minus the, sorry, in the nth interval. It's not to the power n, by the way. Okay, it is in the nth interval, the final error that is obtained. Here we have XR minus XL divided by XR. So that is a relative error. Remember the lecture about
Yes sir,
errors?
yes sir.
So
No
this
sir,
is,
I was telling that there are two types of termination criteria, right? One is that the interval is specified than the predefined error limit, and the function fx tends to 0. So
okay.
so I am
Okay. So here, that is the termination criteria. Okay, epsilon A and epsilon T. It's a mistake on my part. I should not have written epsilon T, because this epsilon, it makes it seem that it seems that
Yes,
this
sir.
epsilon T and this epsilon T are same.
Yes,
It is
yes.
not same. Okay.
Okay,
Probably
okay,
I
sir.
should have written it, say, capital ET or something like that. Some other notations
Yes, sir.
should
That
have
was
been
my
given.
confusion.
Okay. Okay, I understand. Let's move forward. Now, this slide highlights what are the advantages and disadvantages of the bisection method. One of the biggest advantage is that convergence is assured. As long as that intermediate value theorem is satisfied, it indicates that within that interval there is a root. And the root is always enclosed or bracketed. Each iteration brings the approximation closer to them. There is no way that you are going to consider a interval which does not contain the root. If you apply it appropriately, then your search interval always contains the root and convergence is assured. The second advantage is more general, that is more general to iterative methods, I should say, that it has control over error. We have discussed this previously. Why it has control over error? Because we are defining our termination criteria in terms of the relative error itself. So increasing the number of iterations always yields more accurate. So if you increase n, that means the factor 2 to the power n also increases. And that means the search interval is getting smaller and smaller. If the search interval gets smaller and smaller, obviously you are more closely approaching the actual solution. So that is what is meant by the control over error. Inherently, these methods would reduce the error below the specified limit. But there are certain disadvantages as well. What kind of disadvantages? Slow rate of convergence. Here, the convergence is assured, but it approaches the solution quite slowly. There are other numerical methods which approach the solution in an exponential manner. Whereas in this case, in each iteration, the interval gets only half, which means that it's a linear convergence rate. So it's a slow convergence process. The second disadvantage is that if one of the initial guesses is close to the root, it takes a large number of iterations to reach that. There is no way to detect whether the root is in fact very close to one of the edges of the interval. So that is a problem. Now the next 2 points, they are not basically disadvantages. I should say they are limitations of the bisection method. There are situations where bisection method cannot be applied. Suppose a function is such that it just touches the x-axis. Then you cannot find appropriate bracketing values for that kind of function. And this is where the method fails. Consider this example. You can see that a parabolic curve, it just touches the x-axis at x equal to 0. If you suppose you are going to apply the bisection method here, what could be an appropriate interval? I can take XL over here. That is the left-hand side. We have a positive value here. The other side here, that is XR. that is also positive. So it obviously does not satisfy the condition for the intermediate value theorem. But you can see that here at this point, this fx does indeed become equal to 0. So there is a root at this point. But bisection method will not be able to find this kind of a root. So that is a limitation for this method. Another limitation is that this method cannot be applied if the function becomes discontinuous within the search interval. Consider this example. At x equal to 0, there is a discontinuity. So the bisection method also fails for such situations. As I said, the last 2 points are basically not disadvantages but limitations of the bisection. Now let us come to an example. Let's take a numerical value and try to solve this and see how the bisection method actually approaches a solution. If you have a pen and paper with you and a calculator in hand, you can also try to solve this as I go along solving this problem.
Sir, 10 to the power 3 is the pre-specified error limit, right, sir?
Yes, the accuracy is provided.
And it will be
But-
given in the question.
Yes, the
Okay, sir.
pre-specified error limit is usually supplied in numerical problems. Obviously, when you are going to implement a code to solve this problem, you may keep it as an user input. The user needs to provide the pre-specified tolerance because he has the actual problem. That means he decides on how much accuracy he wants in his solutions. Okay. So here, what is fx? This nonlinear function is x cubed plus 4x square minus 10. That is our function. XL and XR obviously given. XL is equal to 1. XR is given as 2. The accuracy is also provided. This 10 to the power minus 3. So at the beginning, we might carry out a quick calculation to see how many iterations are going to be required to achieve this kind of an accuracy. So we know the formula, that is log of XR minus XL. By the way, this is 2 minus 1, so 1. Log of 1, that goes to 0. We have log of, say, E t divided by 2. This is 1, as I said. So n would be, this is 0 minus log of 10 to the power minus 3. That makes it minus 3, and there is a minus over here. So that gives us plus 3. So plus 3 divided by log of 2. So n becomes greater than equal to, if I solve this, I've already got the value calculated. It is 9.965. So obviously number of iterations are going to be integer values. So the next highest integer is going to be the required number of iterations. So here 10 is the required number of iterations. Okay, so we have to carry out 10 iterations of this. Obviously, I'm not going to do 10 iterations. It is going to take time, but at least 1 or 2 I can try to do here. But first of all, here we need to check whether the condition is satisfied or not. That is, f of XL multiplied by f of XR, it has to be less than 0. So what is f of 1? This is 1, 4, 5, minus 5. So minus 5 here, and this is going to be 8. So this is 16, 24 minus 10, this is 14. So this one is negative, this one is positive. So obviously f of 1 multiplied by f of 2 is less than 0. So there is a root, you can say at least one root in this interval 1. Okay. Next, we have to calculate the midpoint of this interval, xm. This is going to be 1.5. And what is f of xm? That is f of 1.5. Let me see what is the value. This is 2.375. So I think if we tabulate this, this will be much easier to understand. Let's write I, that is the number of iteration, what modification we are making to the interval, and here we will write XL, here we have XR, let's write f of XL, let's write f of XR, then we write XM, and finally f of XM. You can also calculate the error. So at the initial position, the starting point, this is 1, this is 2. F of x1, xl we have calculated as -5. This is 14. From here we have got 1.5 and this is 2.375. I'm not calculating the error, I'll leave that up to you. So now what changes are to be made? If we move on to the next, we need to consider this f of xl multiplied by f of xm is less than 0. If we consider this logical condition, then we see that this is indeed less than 0. That means we will get rid of the right hand side. We'll move the right hand side. So let's write it as XR moves to XM, or you can say it the other way. So here 1 remains unchanged, that is the left hand side. This one becomes 1.5. So this is unchanged, -5. This is 2.375. So as you can see, previously it was 1 to 2. Now it has become 1 to 1.5. So the interval is already half. Now we go for the next iteration. Midpoint between 1 and 1.5 is 1.25. We will put this 1.25 in the function. And what is the value? Let me just check here. That is going to be minus 1.79687. So we go to the next one. And now we see that this is a negative value. F of xm has a negative value. F of xl is also a negative value, -5. So that gives us a positive value. So this condition is not satisfied. So we will shift the other end. Now this means that xl will come to xm. So this changes now. This one remains unchanged as the previous one. This is 1.79687. This is 2.375. And we go to the next one. what should be the next one? Next one is going to be 1.375. We'll calculate this value as well. Like this, you will continue up to say 10 number of iterations. So you can see that we are approaching the solution, but in quite a slow manner. So that is one of the disadvantages of the bisection. But it surely is going to converge to that value, because in each of the iterations, the search intervals are reducing by half an hour. In fact, I can tell you what the exact solution for this, or exact root of this equation is. One of the exact roots is 1.36523, something like that. That is the exact value. You can see that we have already come up to 1.375 after 3 iterations. But it will require 10 number of iterations to achieve the provided accuracy. Any questions from here?
No, sir.
Understood?
There are 3 number of routes, right? So can we tell that what route we are approaching, or it one of the 3?
It is one of the 3. In fact, here the problem has been made simpler because you are provided with the search interval. That search interval is already provided. So you do not have to worry about whether whether you are looking for route number 1 or 2 or 3. If it was not given, then obviously you have to find out the search interval.
Okay, sir.
Sir, by numerical analysis, can we find all the 3 roots in this equation?
Yes, but you have to run this program 3 times, or you have to solve it 3 times, 3 different times with 3 different intervals.
Yes, sir.
So we have to increase XL or decrease XR.
Yes. In each iteration, you are either increasing the XL value or decreasing the XR value. You are moving towards the root.
Sir, in your previous slide, you have mentioned one condition that if somehow the in bounding values, if the function gets 0, then how can we counter the situation? Like if fx1,
Yes.
sorry, if f1 equal to 0 or f2 equal to 0, then how can we
Yes,
counter
you
that?
put another condition check, if else statement. If f of x1 is equal to 0, then x1 is a root, and stop the iterations there.
Okay, sir.
Okay. If f of xr is equal to 0, then xr itself is a root, and you stop the iteration. Okay. But here, very important thing to keep in mind is that in case of numerical calculations, it is almost impossible to consider something exactly equal to 0. So that is why you have to keep a tolerance value. If f of xl is less than or equal to, say, 10 to the power minus 7.
So we have to use that FABs.
Yes, sir. Yes, actually, in some programming in our second semester, we have done such things, sir.
Yes, you have to consider that.
Sir, it happens
You
because
cannot-
of the floating point representation.
floating
Yes,
point is
because of the
problem,
floating
sir.
point representation.
Sir,
that is
when
what-
we should increase XL?
Sorry, can you repeat that?
বলছি এক্সেলটা স্যার কখন বাড়াতে হবে, মানে এক্সেল আর এক্সেল?
দেখো, সিম্পল সিচুয়েশন হচ্ছে যে তুমি প্রোডাক্টটা কনসিডার করলে, প্রোডাক্টে যদি তুমি দেখো যে ইট ইজ giving you a negative value, that means it has the root within that. ওকে, এবার তোমাকে দেখতে হবে যে তুমি কোন কন্ডিশনটা কনসিডার করছো। Let us go to the next slide, and there I think when we write the algorithm for this, then it becomes just a little bit more clear. To answer your question, that when we should increase the XL, you see that this condition has been provided already. That is the condition check. This is the condition we are checking. So if this is equal to 0, then you change XR. That means you reduce XR to XL. If this condition is not satisfied, then you increase XL. Is that clear?
Yes, sir. Yes.
So now let us consider a basic algorithm that can be developed for this bisection. Of course, we start with step 1. Step 1 is take input. So let's write input. In this input, you will read what are the quantities, parameters, quite obviously XL and XR, and let's say epsilon t. That is the pre-specified error. Here XL and XR are the two starting values which enclose the desired root, and epsilon t is the error, pre-specified error. Once that is done, you can now go to calculation of fxl, and that will contain this value. Also fxr, which will receive the value of xr. You can here also initialize an iteration counter. This is an iteration counter. It will keep track of how many iterations you are performing. Next, you check this if sine, writing it like this, fxl is equal to sine fxr. Then what needs to happen? These two signs are same. That is not an appropriate interval, is it? So then, if this is true, you write starting values or initial guesses, let's say unsuitable. And then you can stop the program. Or you may have an option of going back to the input and asking for a fresh initial, say, search interval, XL and XR, where the condition is satisfied. And if this condition is not satisfied, then that means it's okay. The search interval is okay. It contains a root. How do we find the root now? Let's take this while loop. While this value, XR minus XL divided by XR into 100 in terms of percentage. If this is greater than or equal to, let's say, epsilon t, then what do? Then we have to carry on the procedure. Here we have considered greater than sign. while this error value, approximate relative error, is greater than this error limit, we continue the iterative procedure. So if that is satisfied, then let's say number 6, write it here, inside this loop, and do this. You just implement XM. That is, XM is found out to be half of XR plus XM. Next step, find out f of XM, which is this. Remember the iteration counter? You increment the iteration counter like this, I equal to I plus 1. And in the next step, you have to consider this. So if f of XL, f of XR, sorry, this is not XR, this is XM, is less than 0, then XR is equal to XM, f of XR is equal to f of XR. Else, XL goes to XM and f of XL goes to f of XR. Sorry, XM. So that is what you do to end the if-else statement here, and this continues till this is greater than or equal to epsilon t. When it falls below, obviously it will exit the while loop and go to the next statement. The next statement here, sorry, I'll write it here. And the next statement is you write solution converged. You can write the root as well. So you can write XM, the final root. You can also write I, that is number of iterations. And at the end, you stop this. So this is a basic bisection algorithm. It does not consider any of the intricacies, any of the complications, does not take care of them. And a straightforward implementation of the bisection method is shown here. I hope you will be able to convert this to a working program.
How will you get the function, sir? In input, we just tell Excel.
No, input function. No, input function will have to be provided in the given problem.
Okay, okay. Sir.
So fx will be provided. Without that fx, it's difficult to implement. Okay. So next is the Newton-Raphson method. I have already discussed the bisection method in quite a bit of detail. I'll try to quickly go over the Newton-Raphson method, and I'll see that this is a much more faster algorithm, faster method as compared to the bisection method. So it is a method for finding successively better approximations to the roots of a real valued continuous function fx. So it is, as already mentioned, an open method That means the root is not bracketed. You do not provide two initial guesses. What you do instead is provide one initial guess. You start from that value, and with that single guess, you start the iterative cycle and progressively approach the actual solution. Disadvantage of this open method is that convergence is not guaranteed. There are situations where the method does not converge at all. But if it does converge, it does so in a much faster way than the bracketing methods. The convergence is faster for Newton-Raphson method. So if I say what exactly is done in this method, then we can simply state that it is based on the principle that for an initial guess, x1 of the equation fx equal to 0, intersection of the tangent drawn to the curve from f of x1 and the x-axis provides a better approximation of the root. We have an initial guess x1. We have the functional value f of x1. From the point f of x1, we draw a tangent to the curve fx. Where it intersects the x-axis, we consider that as a better approximation of the actual root. Maybe just a little bit difficult or complicated to understand. To clarify, let us look at this presentation. We start with somewhere around this value x1. So this is fx1, got the tangent, intersection is here. This is x2. From here, we get the f of x2, we get the tangent again, and like that it proceeds. So this is the way that Newton-Raphson method actually approaches the root. Root of fx is present here. And you can see it surely approaches that root with these tangents and intersection point of those tangents with the x-axis. We'll try to explain that in a better way in this particular graphical representation. Let's consider this arbitrary nonlinear function fx, a general function which is continuous. As already mentioned, the iterative cycle is initiated by choosing an initial guess x1. This is the x1 value, and corresponding to x1, we have the functional value of f of x1. What we need to do is draw the tangent to the curve fx at x equal to x1. So that means from that point of f of x1, we draw a tangent, and that intersects with the x-axis at a point x2. And you can quite clearly see that x2 is in fact quite a bit closer to the actual root as compared to the x1. The actual root is right here. And you can see x2 is much closer to it than x1. So that is the logic that we follow in Newton-Raphson. That is how we approach the root. Next, what we do? Let us find out the slope of that tangent. Find out tan theta. Slope at x equal to x1 for fx. It can be very easily obtained from the definition that this tan theta is f of x1 minus f of x2 divided by x1 minus x2. Now, what is f of x2? sorry, I should not say f of x2. That is this value. Actually, we are talking about this tangent. This is the angle theta. So if we consider this tangent, then in the denominator, it will be x1 minus x2. And in the numerator, it will be f of x1 minus this value. What is this value? That is 0. So we put 0 over there. So as a result, we simplify this expression as something like this. If you simplify it, you bring x1 minus x2 over to the right hand side, put f dashed x1 below f of x1, and then get x2 as x1 minus f of x1 divided by f dashed x1. So x2 serves as the next guess. We repeat the process, go to f of x2, get x3 and f of x3. From there, we go on towards the root. If we generalize this, sorry, if we generalize this formula, then get this. That is x of I plus 1 is equal to xi minus f of xi divided by f dashed xi. That is just the generalized form of this equation. This is known as the Newton-Raphson formula for solving nonlinear equations of the form fx equal to 0, and it gives the I plus 1th approximation with respect to the ith approximation. xi plus 1 is the I plus 1th approximation, and xi is the ith approximation. That means xi plus 1 is the present approximation and xi is the previous approximation. On the basis of the previous approximation, the current approximation is determined. If you look at this expression, all the things, all the parameters on the right hand side, xi, f of xi, f dashed of xi are supposed to be known. These are known quantities. Now you might question that how do we know f dashed xi? You have to carry out symbolically. That means once f of x is given, you differentiate it with respect to x, you get f dashed x. And then you can calculate the values of f of xi, f dashed xi when xi is known. So once the right hand side is known, you get the next approximation as xi plus 1.
Sir,
Yes.
sir, in our C compiler, is there any library function by which we can get the direct derivative of the given function?
At this point, I would suggest that you just carry it out by hand symbolically. Get the expression for the derivative, use it as a function,
Okay,
a separate function. Okay.
sir. Okay, sir. Okay, sir.
This is in fact one of the disadvantages of Newton-Raphson, that you have to carry out the derivative. Now here, do note that we are using f dashed x in the denominator. You do not have too much control over f dashed x. It is possible that f dashed x might become 0 or it may become very small in the course of the computations. And if that happens, then Newton-Raphson method does not work. That is one of the limitations of this method. The next obvious question is when do we stop the iterative cycle? One way of stopping this, if the two successive values of xi are nearly equal within a prescribed tolerance. That is another way of saying that the relative approximate error has fallen down below the pre-specified limit. So this is the termination criteria. Current approximation xi plus 1 minus the previous approximation xi gives you the error. The relative error is obtained by dividing the error by xi plus 1, that is the current approximation. You convert it to percentage and then compare it against the epsilon a value, which is the pre-specified error limit. Now, the previous derivation of the expression, Newton-Raphson formula, is from a graphical point of view. There is also a derivation possible from the Taylor series, which is an analytical case. But for that, are you familiar with Taylor series?
অ্যাকচুয়ালি স্যার এটা আমরা করেছি, মানে আই মিন আই থিঙ্ক এটা স্যার ওই ইন্টারপোলেশন, নিউটনস ফরওয়ার্ড ইন্টারপোলেশন, ব্যাকওয়ার্ড ইন্টারপোলেশন, এগুলোতে
Yes.
করেছিলাম আমরা এই ব্যাপারগুলো।
Okay, okay. So you have already, you are familiar with Taylor series.
Yes,
So
sir.
here,
Taylor Maclaurin, yes. We have
yes,
done.
okay, fine. That is what I wanted to know. It's a very simple process. You have the general function fx, and if you expand it using the Taylor series, it can be written like this. This is the form. What needs to happen is just you keep the first two terms, consider a two-term approximation, and disregard or discard everything from here. So whatever remains, this part, you take it like this, and you can already see that it has f of xi plus 1, which is equal to f of xi plus f dashed xi multiplied by xi plus 1 minus xi. Now, this is supposed to be the root. The objective is to find out the point where fx is equal to 0. So the current approximation or the current value, it can be assumed that f of xi plus 1 should be equal to 0. That is the assumption, because we are trying to find out the root of the equation. So if we put 0 here, that approximately equates to this expression, and that can be manipulated to give you the Newton-Raphson method formula, which was derived previously using a geometric method. So if you go through this, it's a very simple technique. I'm not going to explain it in too much detail. The slides will be provided to you. Just have a look through that. But one thing that needs to be discussed in just a little bit of detail is the choice of the initial guess, because it is very, very important in case of Newton-Raphson. As already mentioned, that the convergence is not gap, and if the choice happens to be not an appropriate one, it is not close to the actual root of the function, the equation, then the method might not converge at all. It might move very quickly out of the bounds of that particular root. On the other hand, if the choice is an appropriate one, it is near to the root, then this technique converges very, very fast. I have already told you that a wrong choice of the initial guess can lead away from the root, and it may even lead to an infinite cycle. It might fall into an infinite loop. Let me just...
Sir, is there any particular method to choose the initial guess, sir?
I will come to that. Let me just discuss some of these details, then I will come. This is the first example that I will consider. You can see here the function is given, graphical representation of the function. This is fx, a nonlinear function. You have the root over here. That is the root. We have started with a guess of x0 from here. So we get a tangent. Draw the tangent here. There is x1. Next approximation. We get the fx value here. Get the tangent. This is x2. Extend up to the curve. Get the tangent. And see what happens. It progressively, in fact, leads away from the root. This is not altogether an inappropriate choice. Means it is quite possible that you can get this as the initial guess. But this sort of a problem happens if the function has an inflection point. What is an inflection point? This one is an inflection point. Here you can see that the curve changes its curvature. Previously it was, let's say, concave, becomes convex after that. So if there is an inflection point, Newton-Raphson method fails. And you will see that nature of the tangents are such that progressively, instead of giving improving approximations, it gives worse and worse approximations. Next, consider this case. We have a curve like this. This is fx. This is x0. A reasonable approximate guess. This is f of x0. This is x1. From here it comes here. And then see what happens. The tangent becomes almost parallel to the x-axis. So the next guess that you will get is going to be a huge number, or it approaches infinity, positive infinity. Why does it happen? Because here you see that the derivative f dashed of x1 is very, very close to 0, almost equal to 0, because it's a local minimum. So the first derivative is close to 0, or in fact 0 itself. So in the denominator, you have this very, very small number. And what will happen next is that it will blow up the next guess to a huge value. So whenever the derivative becomes small, it becomes sufficiently small, then the Newton-Raphson method fails as well. So you have to be careful about such situations and keep a check probably to guard against such things happening. You should keep an if-else statement within the loop where this derivative is calculated to check for whether it is falling below a pre-specified value or not, small value. If it is falling below that, then you should terminate the program. Otherwise, it is going to give you an erroneous value. Next, have a look at this one. We have started with this x0. That is the initial guess. The expectation is that probably it will either reach this root or this root. That is, there are 4 roots here. Starting from the right hand side, you see here this is xr1, xr2, xr3, and xr4. As you have given this approximate initial guess closer to the first and the second root, xr1 and xr2, you expect that it will approach those roots. But what happens here is that the tangent takes it to here, that tangent takes it to here, and you don't know where the next tangent is going to be. But the outcome is that it progressively leads away from all these roots. This is known as root jumping.
Sir,
Yes.
sir, ঠিক আছে.
Okay. Next, consider this situation. Here there is an oscillation about this local minima. There is a local minima over here. The approximate guess that is provided is here, x0. So you can see the tangents are such that it comes over here, it starts to oscillate about this local minimum, and then finally goes away. Whereas the root is completely in another direction, the opposite direction. It may also happen that if such a point is there, and you have given this as the first root, then it might come over here. It goes over here. Then it takes it back to this position. So it falls into an infinite cycle like this. It will move around these two values infinitely. So whenever you implement a code for Newton-Raphson method, there should be a limit for the highest number of iterations, maximum number of iterations. You should go for a for loop using a maximum number of iterations such that it forcibly ends the program after n-max, n-max being the number of maximum iterations. So these are the sort of problems that can occur if you do not have a appropriate initial guess. But the next question is, how do you know what is an appropriate initial guess? It is always a good idea to, first of all, run bisection method. In bisection method, convergence is guaranteed. So you cut down the initial interval to a smaller value. Then with one of the say interval values, that means either XL or XR as the initial guess, then you run the Newton-Raphson. So you approach the root using the bracketing method, and once you have got a sufficiently small interval which ensures that there is a root in between those 2 points XL and XR, you start the next step of the procedure, which is the running of the Newton-Raphson method using one of those 2 interval values, XL or XR, as the initial guess. That will refine your solution and give you high accuracy. So that is how you get an idea of an initial guess. Now this is the same problem. I think we have taken off quite a lot of time for today's class in discussing these things. I'm not going to solve this problem right here. I'll give this one as a home assignment to you. You should carry out this problem, solve this problem using Newton-Raphson method, compare it with how we obtained the solution for the bisection method, and see how fast this Newton-Raphson method converges as compared to the bisection method. So this is a home assignment. You should solve this problem by hand. This is also given as say an assignment. As an assignment, you should write down a workable algorithm for the Newton-Raphson method and submit it before the next class. So you have 2 different tasks. You solve those problems. The bisection method, complete solution should be there. The Newton-Raphson method solution should be there. The same mathematical problem solved using 2 different techniques, and you develop an algorithm for the Newton-Raphson method. So I hope that is clear to you.
মানে স্যার হ্যান্ড ক্যালকুলেশন করতে হবে, তারপর ওটাকে মানে ওই এতে কম্পিউটারে ইমপ্লিমেন্ট করে আপনাকে দিতে হবে।
Algorithm. You do not have to write the program as yet. I have not told you about it.
ও আচ্ছা, অ্যালগরিদম, ঠিক আছে।
Write the algorithm.
অ্যালগরিদমটা কি হাতে লিখবো না?
হাতে লেখ। Write it by hand. Do one thing. This is let's take it as a sort of a class performance. Okay. You solve the problems as soon as possible. Write down the algorithm and submit it to me by tomorrow. Okay.
Okay, sir.
So that's all for today's class. Thank you.
Classroom is submit to sir?
Yes, in classroom. Submit it in classroom. Okay. Now I have a meeting to attend from 1 p.m. So the meeting has already started.